Okay, in this video, we're going to find all the roots or zeros of the following polynomial function. So this is more than just finding the rational roots, although that's what we're going to start with. We're going to find all the roots. These could be rational, which we'll identify first. We may run into some irrational, or even imaginary will eventually be possible, those non-real complex results. Zeros that turn out to not be x-intercepts would be your imaginary zeros. All right, so just for starters, notice this is a cubic polynomial. So we know we're looking for at most 3 unique zeros. So we're going to utilize the Rational Zeros Theorem and get started with our analysis here, looking at the P over Q list as we discussed in class on Monday. Okay, so the Rational Zeros Theorem, generating this P over Q list. Again, this just represents the possible or potential rational zeros. And P comes from the factors of the constant. And Q is coming from the factors, the Q values are the factors of the leading coefficient. I abbreviate that L/C for leading coefficient. All right, so let's take a look at this particular problem. The P over Q values, and make some room here to work. Let's get started by listing the factors of negative 72. Okay, now 72 actually has quite a few factors. So one way you can kind of streamline the process here, instead of writing so many plus or minuses, I'm going to kind of just do a distributive plus or minus, and then I'm going to list all my factors of 72 inside of this, just to cut a little corner. So we know 1 and 72, we know 2 and 36, oh man, 3 and 24, 4 and 18, 5, I don't believe so, 6 times 12, 7, no, 8 and 9, and I think that does it. Okay, so we'll start with just those. I think I got them all. And then let's look at the factors of the leading coefficient. Those are going to be the factors of 10 in this case. So again, plus or minus 1 and 10, 2 and 5, a lot shorter list. But we've got our work cut out for us. So what I'm going to do is I'm going to move down the page here and try to get an idea of all the possible combinations this makes. So just like we did in class the other day, I'm going to start by holding one denominator value at a time and considering all the numerator values. So I'll get 1 divided by 1, and then 72 divided by 1, 2 divided by 2, and so on and so forth. So I'm going to try to quietly get this written down real quick. Okay, the next thing I'm going to do is look at what if we divide by 10. And as we go through this process, we will run into some things that need reducing and maybe even some redundancy. So we'll get 1 over 10, 72 over 10. Worry about reducing this on our next step here. 2 over 10. I picked a giant set of numbers here, didn't I? 36 over 10. 3 over 10. You could probably scrub forward in the video if you know how to do that. but I will try not to make any mistakes and leave any values out. And we'll reduce these fractions that can reduce and cross out redundancies next. Oopsies. Alrighty. Get the, whoa, that's not the pen I thought it was. There we go. All right, now we'll go after 2 as a divisor. That'll be 1/2, 72 halves, 2 over 2, 36 over 2, 3 over 2, Okay, so we've taken care of 2's, taken care of 10's, and we've taken care of divisors of 1. So the last one here, I'm going to switch back to green. We're going to go after the divisor of 5. That's everything in the numerator divided by 5. And this should create quite a few unique results we haven't seen repeated in our list yet. A good thing to remember is, even though this is a long list, lots of fractions here, probably quite a few redundancies we'll clean up here in a second. This is still an amazing way to sift down from, hey, it could be anything. These rational zeros, when I first look at this cubic without having graphed it, using the Rational Zeros Theorem and sifting it down to a finite list of numbers of possibilities that these nice rational zeros, if they do exist for this function, come from this much shorter, oopsies, talking and writing, much shorter list. Okay, so now the task is we need to go back and start cleaning up which of these are reducible and which are redundant. So I'm going to just start back at the beginning of the list and start writing out what we have, kind of a final copy, if you will, for our P over Q list. And that's 1, 72, 2, and we'll get going here, and then eventually we'll run into some fractions we can reduce and also some things that are popping up more than once that we don't need to duplicate. That happens quite often. Okay, so now we're into some fractions. We'll be able to start reducing some of these. 72 tenths, I could take 2's out of that. That'll be 36 fifths. And we can reduce 2 tenths to 1/5. 36 tenths, that'll come down to 18 fifths. Then 3 tenths, so that's a new one. 24 tenths, 12 fifths. 4 tenths is 2 fifths. The farther you work through a list this big, the more frequent you'll run into repetition. All right, so I'm over here now. 18 tenths would be 9 fifths. Haven't had one of those yet, so 9 fifths. Distributing this plus or minus saved me quite a bit of writing. 6 tenths will be 3 fifths. That's the first time we've seen that. 12/10 will be 6/5. 8/10 is 4/5. 9/10. All right, we've had just about all the tenths and fifths here. Now we get to 1/2, and I believe this is the first time we see a half. Okay, 72 halves is 36. So there's the first thing I can cross out. That's a redundancy. 2 halves also reduces to 1, so that's redundant. 36 seconds, that's just 18. 3 halves, that's going to add to our list. 24 halves, that's 12, so no need to duplicate. 4 halves, also a duplicate. 18 halves, that's 9 again. 6 halves, 12 halves, duplicate, duplicate. 8 halves. 9 halves, I think, is a new one, so I'll put that down. Okay, then on to 1/5. Oh, 1/5, pardon me. We had that earlier, so there's a redundant. 72/5, though, we have not seen that. 2/5, yes, that was at the end of the last line, so that's a redundancy. 36/5, been there, done that. 3/5, 24/5, I think is new. 4/5, that's a repeat. 18/5, 6/5, repeat, repeat. 12/5, repeat. What about 8/5? Okay, 8/5 I don't see. And 9/5, also a repeat. Okay, folks, so this is, if you count them up from beginning to end here, 1 through 8/5. How many numbers is that? 1, 2, 3, 6, 30. And when you include the plus or minus, which is real key, you either need to handle that on every single number you write or put it distributively outside a parenthetical layer. You get a total of 60 numbers here. Okay, so I'm going to grab a hold of that and we're going to take this list with us. So this is what we call step 1. And let's see here, copy that. Okay, so step 1 is just getting all of your P over Q values, and that's this P over Q list. And it can be a little tedious when the numbers have a lot of factors, like we did here. So 72 really loaded up some factors, and then 10 had 4 factors. So it just took a minute to do the accounting. But this is what we're looking for, this P over Q list here. Okay, let's take a look now at the step 2, and this is going to be where we graph and check. And let me see if I can get this to fit. There we go. All right. Yeah, that is large. Okay, big list. And so what we're going to do to graph and check is first enter it into the graphing calculator. Now be careful to do that correctly, get all your signs right, and then think about the size of the numbers here. Okay, so you could start with a fairly conservative window. I mean, we do have as big as 72 and negative 72, but most of these values are fractions, okay, are going to land kind of in this, 2, 3, 4, 6, a lot of things under 10 and even under 4 or 5 here when you think about some of these fraction values. So what I would do is just start with a rather conservative window. We could always make it bigger. I went with negative 10 to 10 because I would get most of these numbers to show up on the x-axis within that span. But you could have started with negative 75 to positive 75 and really would have struggled to see much here. We could tell that the zeros we're trying to find are somewhere between negative what is that? -4 and -5. We've got another one that looks like it's right at -1. We'll have to trace that. And then another one here between 1 and 2 here. So we're not sure exactly what these are until we check with tracing. Notice that I did make a pretty large scale for the y values. This is a cubic with a leading coefficient of 10, so it has potential to be pretty steep. So I just made a larger y-axis, kind of zoomed out y-axis. Okay, so we are going to look at our list of potential. These are just possible zeros. And what I notice is back here, right at -1, I noted this already. And -1 is one of our first values in the list. So if we trace to that precisely, we're going to get a, here it is, bottom left corner of the screen, we're going to get a confirmed x-intercept. So I'm talking about the trace feature on your TI-84 or TI-83 graphing calculator. You want to hit trace, and then after that you hit -1, enter. Okay, and that'll show you a 0, meaning you're right on the x-axis. The other values we run into, this one looks like -4.5 back here. And if we double check our list of potential zeros, -9/2, there it is. 9/2 is on the list, so plus or minus 9/2. So when you trace to -9/2, hit enter, boom, you get your 0. Now, there's one more, and you can see it on my screen here already, at 1.6. So 1.6, or you could, if you're looking at your graph, 16/10, that's 8/5. Okay, is that in my list? So, that's a number that's between 1 and 2. So you're really kind of just hunting through all these values. Between 1 and 2, I would have 9/5, and I would have 8/5. I'd have 3/2. I'd have 6/5. So really there's 4 numbers, positive values, that would land on that possibility there. And sure enough, when you trace to 8/5 and hit enter, your calculator will confirm a 0 there as well. Just a quick footnote, these didn't do it for me, but sometimes on your graphic calculator, you'll get an x value, say it did it this time at 1.6. And the y value, occasionally you'll see this garbage number like -1.511 E12, something like that. And this is scientific notation, and basically it's round off error in the calculator. If you think about what this is, -12, I should say. What this scientific notation is saying is, that's an incredibly tiny little decimal with all these zeros, and then this 1, 5, 11. So round off error, it's basically 0. Okay, so you shouldn't run into that too often, but it does come up from time to time. Okay, so here's a quick turnaround. We have done 2 steps, and we found 3 of our x-intercepts, 3 rational zeros. So step 3 is going to be state the actual rational roots. Okay, so this is just a finalizing statement that says my actual or verified rational roots happen at x equals -9/2. I like to stick with fractions. +8/2. Sorry, that was 8/5. And the other one was -1. So we verified these by tracing. They came from our list of possibilities, and we used the graphing calculator to do the work of verifying. So you'd want to say that at the end. The other thing I want to point out, and this is just a teaser for the next video, is this was a cubic function to begin with. Remember that? It was a 10x cubed, a bunch of other terms. So back to the fundamental theorem of algebra. If we have a degree 3, we will have at most 3 unique zeros, or 3 zeros if you count multiplicity. And here they all happen to be rational. So our search is over, okay? If the number of actual rational roots found, including multiplicities, is less than the degree of the polynomial function, then we have more work to do. We have more zeros that are hiding for us, okay? So if this is less than the degree, then we go to step 4. Now we found 3, 1, 2, 3 zeros, and this was a 3 degree, so that means we're done. And we do not need to continue on to step 4, searching for irrational or non-real complex.